In this unit, we have been looking at objects in motion, and in Chapter 13 in particular, we've been looking at acceleration. You have learned to make 3 different types of graphs to represent motion of an object, and in this section, we're going to be looking at how those graphs are related. There are 3 types of graphs illustrated here. You can have a distance versus time graph or a position versus time graph to show the motion of an object. You can have a velocity versus time graph or an acceleration versus time graph. All 3 of these graphs represent the motion of a single object. They're all showing the same thing. If we look at them again, if we look at this position versus time graph, you know that on a position versus time graph or displacement versus time graph, the slope gives you velocity. Because this is getting steeper as you go, if you wanted to figure out the slope, it would always have to be instantaneous. And it would be getting steeper as you go. And if you translated this over to a velocity time graph, you would get an increasing velocity, like such. You know that the slope of a velocity time graph is acceleration. This has a constant slope. This line has a constant slope the whole time. So you can find that value. It means it has a constant acceleration. So to summarize, the slope of a position time graph gives velocity, and the slope of a velocity time graph gives acceleration. You know that the area underneath a velocity time graph would give displacement, and the area under an acceleration time graph would give velocity. Let's look at an example. Figure 5, this figure here, shows the motion for 30 seconds of a person riding a motorcycle. And this question wants us to determine the displacement of the person during the time shown. And this is a velocity time graph. So we know that displacement is going to equal the area under graph, or area under line. But if we look at this, it's not going to be a nice area. We can make a rectangle here, but then we also have this triangle to deal with, and another rectangle here. So when we have a complicated graph like this, or one that doesn't just break apart into 1 or 2 nice shapes, I like to number them. So we'll have area 1, area 2, and area 3. To get the displacement, you need the total area. So we'll solve all 3 and add them together. Number 1, area of that shape, it's a rectangle, so it's going to be length times width. So area in this case, it goes up to about 22 meters per second. So we'll say 22 meters per second multiplied by the width, which is, I think, 18 seconds. When you work that out, you get 396 meters. So that's the displacement represented here. For number 2, it's a triangle. So area is going to be base times height divided by 2. In this case, our base is 12 seconds. Our height is 17 meters per second, the difference between 22 and 5, and divide by 2. And that's going to work out to 102 meters. For the third area, we have a nice little rectangle. So area equals length times width again. We get our length from 17 to 30. And our height of, or length, or width of 5 meters per second. So 5 meters per second times the 12 seconds is going to give us 60 meters. Then we need to add all these together. So 396 plus 102 plus 60. And we get 558 meters as our total displacement. Okay, let's look at another example of how we can use graphs. In practice question number 2, we have Brenda and Hillary, and it says that Brenda can run at 5 meters per second and Hillary can run at 7. So Hillary gives Brenda a 25-meter head start in a 100-meter race. And this graph here shows the distance versus time for that race. Hillary's distance is in red, so let's just make a note of that. This is Hillary. And Brenda is in blue. And we want to figure out who wins the race and by how much. So looking at this, we can see from the graph the person who wins the race is the person who's going to get to the 100-meter mark first. And going along in time, we can see that Hillary wins. So we can see by the graph that Hillary wins. So she gets to the 100-meter first by about, and then you kind of need to estimate how far ahead she is of Brenda. So how far behind is Brenda when Hillary gets to 100? And I would say it's about 4 meters. So by about 4 meters. Okay, one more example. And this example is going to get you to draw a graph and figure out the answer to this race. So looking at here, we have Paul and we have Ben. And Paul can skate at 12 meters per second, and his friend Ben skates at 10. And they're racing together in a 400-meter race. So Paul gives Ben a 5-second head start. We want to draw a graph for their motion to figure out who wins. So right away I know I'm going to make a distance or displacement versus time graph. So here I'm going to put the position, and it's in meters east. And we know they have to go a total of 400 meters. So let's make this 400, this will be 300, this will be 200, 100, and they'll start at 0. And it's going to take 40 seconds. If you look at that for the slower one, for Ben, he's going 10 meters per second, so it's going to take him 40 seconds to go that far. So we can just put on a velocity for Ben, like this. And when he reaches the 400 meters, that should be here at 40 seconds. Then we have to figure out how long it's going to take Paul. And Paul's going to start at 5 seconds. And if you work it out, Paul has to go 400 meters. And he's going 12 meters per second. It's going to take him 35 seconds. No, it's going to take him 33 seconds. So he's going to get to 400 meters earlier. He's going to get there at 38 seconds. So we would have to draw him getting there here. And then you would need to go from 5. Let's see if I can use a ruler on my touch screen. I'm not sure how this will work. But we need to make his line like this. Okay, so I should label who's who. So the slower one, Ben. Faster one, Paul. And Paul is still going to win the race. This at the bottom we're going to be doing in class. So please review these notes if you don't understand them. Bring any questions that you have. And we're going to be doing some CYUs working with this stuff.